Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we'll be looking at GCSE chemistry rates of reaction. So as we know, reactions can happen at different rates, so we have some slow reactions such as rusting of iron during exposure to oxygen. We have some sort of medium reactions such as oxidation of magnesium, and we have some really fast reactions indeed. Say if you were to burn magnesium in air rather than water, which would produce medium reaction, whereas in the air magnesium would produce rather violent reaction, especially magnesium powder. So reactions can happen at different rates. And of course that's a very important consideration, especially in terms of industry, where you want your rate of reaction to be as high as feasibly possible, because you want to crank out as much product as you can in as short space of time as possible. But of course sometimes things aren't very that simple, because yield comes in, which is a video for another day, and things like that. However, today I will introduce you to rates of reaction, explain a bit about why those happen, and we'll be expanding on these topics, touching up on these topics in upcoming videos. But today I will just give you a quick intro as to what it is and why rates of reaction differ between reactions, a bit about collision theory, and how to read reaction rate graphs. So without further ado, let's get started. So, reaction. First of all, reaction is essentially where we begin with a bunch of reactants and then we end up with a bunch of products. Product or multiple products indeed. And how fast that happens, how fast we are converting from reactants to products, how much product we can make in a given space of time, say per minute, how much product we can make per minute, or how much product we can make per hour, would be referring to the reaction rate. The rate explains to us how quickly we're making product from reactants. So that's essentially what rate of reaction is. Now, why do we get differing rates of reaction? Why do rates of reaction differ? Why is rusting of iron slow and then burning magnesium powder is literally blindingly fast? Well, one major thing that comes into it is collision theory. Now, you might have heard of collision theory before. Collision theory is a theory that explains why things react, what condition they must fulfill to react. So collision theory tells us that in order for particles to react, they need to collide into each other as they're moving haphazardly. They need to collide into each other. But they need to collide into each other successfully. They need to collide into each other with enough energy to react together. So here I illustrated a bit about how this works in practice. So simply here we have one particle and other particle, they collide each other with enough energy to react, and then they form one product. So that's simple. That's how basically the whole thing works. Now, what if we have two green particles, two red particles colliding together successfully at the same time, and then they end up making two lots of the product? So the rate of this reaction is twice as fast as the rate of reaction here, because we have twice as many particles colliding successfully to create a product. So that's how collision theory explains why different reactions take different times, why they react at different rate. Simply because we have collision theory, and simply because in one reaction we may have more successful collision per second than in a different reaction where we may have less successful collisions per second. Now, here's the emphasis on successful, because if particles collide with each other but they don't collide with a sufficient energy, then simply no reaction happens and there is no extra product being made. These collisions need to be successful in order to react. So the successful collisions are what matters. These collisions are the ones that modify the rate of reaction. And later on we'll be talking about, in different videos, we'll be talking about the different conditions that we can introduce to increase or decrease number of these collisions, successful collisions happening, and therefore modify the rate. So there are many things that can affect this. But that's the basics. That's the basics of what changes the rate of reaction. Now, here we have a rate of reaction graph, and I will quickly show you how to use those, how to read those. So, in the y-axis, we have the amount of product. So the total, this is important, the total amount of product we made. So not the amount of product we're making per second, which some graphs could do, or the change in the product. This is the total amount of product that we have at the end. And here we have time. So generally when we start the reaction, we have zero product. We start with just reactants only. And then towards the end of the reaction, the lines flatten off because we are not making any more product. And if we are not making any more product, we have a constant same total amount of product, and therefore the reaction has finished. We're not making any more. The reaction has finished. So wherever we see a flat line, that means a reaction has finished. Now, what do these lines represent? Well, the black line that I drew right here, that's the, say, original reaction. So that's what we would see in a normal reaction. We start with zero product, and then it climbs. The amount of product increases as the time goes on because the reaction is happening. And then eventually the reaction finished somewhere around about here, and the line flattened out. It flattens off. And that's the original reaction. Now, the green line that we see right here, that green line, that represents a faster reaction. A faster reaction, but the reaction has the same amount of reactants as the original reaction. Right? So it has the same amount of stuff reacting as the original reaction, and that is really crucial. So here we see the green line reaching the point where it flatlines faster. It climbs faster, but it flatlines faster. And it flatlines at the same level that the black line did, the original reaction did. And that is because we made the same amount of product. We have the same amount of product. We have simply we did the same amount of reactants, but they simply completed the reaction much faster. So it flatlines much faster. Same amount, just faster. Red line right here represents, again, same amount of reactants, but faster. Even faster. So the reaction is completed right about here where it flatlines, but again, it ends up on the same level. And the orange line, the big orange line here, that line represents where we chuck in some more reactant. So the rate of the reaction flattens off. I drew this badly, but somewhere similar where the red line is. So the rate of reaction is here the same. However, so here we have a big line, and here we simply are using more reactants. We are using more reactants, and therefore we make more product. And the line flattens off much higher than all of these lines together, because we are making more product in this reaction, because we use more reactants. So that's the two variables here: the rate, which is how fast it gets to the flat line, and how much product we made, or how much reactant we started with, which is shown by how high the flat line actually is. So this is it for today, guys. Thank you very much for watching my videos. I really appreciate you guys watching my videos. This is why I love doing this. If you have any questions, pop them in comments. I'll be more than happy to help you answer them. And if you want to see more videos like this on GCSE sciences and maths, hit the subscribe button below. Don't be shy. If you think this video helped you, give me a thumbs up. Thank you again for watching, and see you next time.